Hey guys, in this video I wanted to focus a little bit on wrapping things up, putting all our concepts together and seeing what we can come up with. So there's really nothing particularly new here except an emphasis on our way of thinking about numbers and functions and making sense of information. So holistically, here are the different things we've been able to talk about: linear, exponential, quadratic, rational, and a little bit about radical functions. And so each of these has its particular use and particular application, and requires, of course, a different understanding or a slightly modified understanding of algebra. So essentially, what's our goal? Well, our goal is typically, when we're dealing with algebra, at least in a two-variable sense, is that we have two variables, right? We want to understand two variables. Our goal is to take two variables, and I'm obviously not writing everything I'm saying here, but two variables, and make sense of the relationship. So in doing so, oftentimes with real world data, we want to be able to say not only how are these two variables related. In other words, as income goes up, or as age goes up, maybe income goes up. But how is it going up? Is it going up constantly? Is it going up more like this? Is it going up more exponentially? I mean, how does age and income, for instance, how are those two linked? And why is that important? Well, data is always important, particularly in being able to, for example, know as a marketeer who you want to advertise to. If you're selling a TV that's $2,000, then you're probably not going to advertise it to 15, 16-year-olds. Well, how do we know that you shouldn't do that? Well, other than the fact that we could probably say 15, 16-year-olds probably aren't on the higher end of the income scale, we should be able to measure that with data to be able to know for sure. Also, things that might affect that are, home builders, for instance. Home builder would probably want to know what kind of age group it's catering to. So if it's, young buyers in their 20s versus buyers in their 30s, then they're probably reaching a totally different demographic and, a totally different income group. And so they want to make sure they can advertise to the right people and make sure that they are building correctly for the right people. So our goal in this whole class is really developing tools to be able to take two variables and make sense of their relationship. Now, we can do that at least, this isn't the total number of ways we can do that, but this is what we've talked about in this class. And there are two ways we can build these. So we have, first of all, we look at typically, in a real world, we have an input and we have an output, and we can express those in pairs, or we can put them in a data table and look at them and compare them and talk about them, and then make the decision of which one of these to apply. So we've done this in two different ways. One is to manually build these. So manually, when would we build them manually? Well, manually, oops, I'll just write a number 1 here, is when typically we have a small number of points. Small data set, manageable by hand. So, for example, if you have if you have a set of ordered pairs, like 1, 2, 3, 4, and even though there are 4 data points there, if your outputs go 5, 10, 15, 20, well, you probably don't need to use linear regression. You could probably find this manually and say, hey, you know what? The change in the output is 5 for every 1 unit change in the input. And so I already know what the rate of change is. It's constant. And so that kind of allows me to really quickly manually build a function. But if it's approximately linear, like let's say it didn't go up by 5 each time, but what if it went 5, 11, 15? Well, now it goes up by 6 here, but 4 here. But maybe we still think the trend, is roughly linear. Maybe it does something like this, but overall you feel like it's a, pretty much a straight line trend. Well, in that case, we would want to use regression, right? If the points aren't perfectly spaced to identify or to build the function. Now, oftentimes in the real world, we use regression anyway, because it doesn't mean that just because you can tell what the function is and what the rate of change is, it doesn't mean that you can't use regression. You can always use regression, but it's important to understand manually how those functions are built as well, because otherwise, if you don't, then regression won't make much sense either. So we have these different components, and we have each function has its different flavor of data, right? So what kind of data would be flavored with a linear function? Well, if the rate of change is constant rate of change. Exponential. Well, exponential, there is something constant about this data, but it's not that the output is increasing by the same fixed amount. It's that we have a fixed percentage increase. So constant percentage, I'll just say CP, you can write that out if you want, constant percentage increase. So doubling, tripling. If you double something, you're increasing it by 100%. If you triple something, you're growing it by 200% beyond what it already is. Quadratic. Well, when do you have a quadratic? Well, when the rate of change is changing constantly. Constant change in slope. I'll just say slope, but slope equals constant rate of change. I don't care what anybody says. To me, those two things really mean the same thing. Otherwise, you just get confused as to what the difference is. So slope and constant rate of change are really referring to the same thing. Irrational, when do we use irrational? Well, that's a little bit more obscure, right? Like, you can't look at the outputs and say, I think this is rational. Sometimes you can, but most of the time, this just depends on, this is typically when you want to build something like an average function, or you want to build a function whose output is dollars per person, or dollars per year, or dollars per month, or people per household. Things like that, where you can model a function for the input, the numerator, and you can model a function for the denominator, and then you divide those two functions, you've created a rational. Radical function, these are kind of a little bit more obvious when these pop up, because, anytime you're dealing with anything like, a squared plus b squared equals c squared, where you're talking about right triangles. Oftentimes, a radical function is basically, as we talked about, kind of the inverse of a quadratic. Whenever you have the square root of something, y equals the square root of x. So these are a little bit more obvious when you come around to them, like, it's usually you're using a specific flavor of that function. You can't really just go into a radical regression. That doesn't really exist. But anytime I can express a function as y equals x squared, I can also say that x equals the square root of y. And so that's a radical function. That's just me taking the square root of both sides. Okay, so what we'll do next is we'll sort of just look at a couple of examples, and I won't tell you which one of these it is initially. I want you to kind of pause the video and say, can I build the model? Can I build an equation? So we are going to do some equation building, or model building. And for us, equation and model in math really mean the same thing. Equation / model building. Okay, so I'll give you the first one. I really want you to pause. I can't obviously tell that you do, and try to think about it and figure it out, but it's a great review. So I'm going to pull this up, and I want you to kind of pause, think about it, write some stuff down, and then pursue watching it. Okay, so here's the first problem. In 2010, the number of Nokia smartphones sold was 23.8 million. According to this website, this represents a 44% increase over the previous year. So there are two questions. What do you think that we want to model here? If you are looking at this data, then what is it likely that you're trying to model? What as a function of what? What do you think the input and the output are? And secondly, what kind of function can be used to represent this data? So go ahead and pause now and think about this. Okay, so I'm assuming you've paused. And now it appears that we're looking at two things. We're looking at the number of Nokia smartphones sold, and we seem to be interested in a time period, right? Because we're saying this represents a 44% increase over the previous year. So it appears that we want to look at the number of Nokia smartphones. Let's give this a value, a symbol of n, and we want to look at as a, based on the number of years. So this is time, and so let's make a couple of notes here. So the input is time, and we're going to measure that as years after 2010, and then we're going to look at the number of Nokia smartphones, and this is in, we'll just say this is in million. We don't actually want to write out 23.8 million. So this is in million, and well, based on this information, I don't know anything other than in 2010. So here's 2010, Here's time, and here's the number of smartphones sold. So in the first initial year, there were 23.8 million phones sold. Here's the beauty of dealing with these with time, is that we can always assume that the first value, or most of the time we can assume that the first value is in the initial year. Okay, so we've got that, and then we're saying this represents a 44% increase over the previous year. Well, why do we care about that? Well, we're going to make an assumption, of course. We're going to say, okay, well, since this is all the information we have, we're also going to assume a 44% growth rate. Now, this is a growth, right? And it represents a rate because it's telling us what happens each year. And so if we looked at the next year, we could probably figure out what's going on. So if I know, let me go to the next page and build a table. And in this table, I'm going to look at time and number of smartphones. I'm kind of have my tablet sideways here. So in year 0, I know there were 23.8 sold. And I'm going to make an estimate for what should happen in 2011. This is 2010. This is 2011. And since I know this is a percentage increase, well, how do I find a percentage of something? Okay, well, to find a percentage of something, we're familiar with multiplying it by taking 23.8, multiplying it by the percentage, which is 44%. And we know that 44% means 44 over 100, which is equal to 0.44. But that only tells me the amount of increase. So if I just did that, then what would I know? Well, I'd know that in the next year, this is the amount, this is the increase in the number of smartphone usages. Well, it looks like I'm multiplying, right? It's not like I'm adding something to, it's not a constant number that's getting added to 23.8, it's a constant percentage. And what do we know about functions that have constant percentage? Well, it's an exponential. So instead of multiplying by 0.44 and just getting the increase, why don't I multiply by 1.44? That gives me not only the amount by which this is going to grow, but also the addition. So I'm working on getting my calculator up here, and let's see what we find. Okay, so we're going to say, and why are we building this table? We're only building this table just to get a sense of how the data is changing. So this is kind of more of, here's my thought process behind how I would begin thinking about what kind of model to build here. Is, okay, well, wait a minute, it's a 44% increase. So next year, I would expect there to be about 34.27 or 34.3, just to be consistent in rounding, million Nokia smartphones sold in that year. Okay, well, is this a good model? I mean, who knows? We could probably look at what actually happened in 2011 and then be able to say, yeah, this was a good estimate or this was a poor estimate. So good. Well, based on the information that we have, that's the best that we can predict. So in 2012, we would expect again to be able to take this number, and since it's whatever occurs in that year, that amount should be growing. That should represent the base of the 44% growth. So again, I'd multiply by 1.44. Well, hopefully we're getting the pattern here that it looks like to determine the number of Nokia smartphones, well, it's 23.8 is the starting amount, and then I multiply it by 1.44 how many times? Well, if I want to know the number of smartphones 5 years later, I would multiply by 1.44, take that, 1.44, take that, times 1.44, and so on and so on and so on. Well, I would keep multiplying by 1.44 as many years as I wanted to pass, and so really we're saying that this is 23.8 times 1.44 to the t power, and that gives us the number of Nokia smartphones. So now we've built a model. Now we could certainly answer questions about it. You know, we could say, okay, so what kinds of questions could we ask? We could say, how many phones are sold in blank year? How many sold in 2015? Okay, well, we can make an estimate. We can say, well, okay, wait a minute, 2010 is 0, 2015 would be 5. Okay, so now I can say 23.8 multiplied by 44% 5 times, and that will give me the number of Nokia smartphones. What else could we ask? Well, we could ask, in what year will the number double from 2010. Okay, well, what do we mean by that? Well, we mean that if there were 23.8 million in 2010, when will there be double that many? So we know that in year 0, we have 23.8, and we want to know in what year will there be double that? Well, what is double that? Now, it's 2 times 23.8, and that appears, I think that comes out to about 47.6. So this is actually just 47.6. Okay, well, how do I determine that? Well, really, what am I asking? I'm asking when is the number equal to 47.6? So I can replace 47.6 in my equation. So I have 23.8 times 1.44 to the t. And unfortunately, we have not developed in this class a way to get the t down from the exponent, because, you know, algebra is just isolating the variable, right? Trying to figure out what value it could take on. We could do some guess and check, but we would probably plug this into our calculator, an initial value of 23.8. It's increasing exponentially, and so at some point in time, here's 47.6. Well, hey, remember how we found this? We could just plug 47.6 into our calculator, plug this function in to y1 equals, plug this into y2 equals, and figure out where do they intersect. The input represents the year, and the output should be 47.6. So this is kind of using our sense to come up with some details for how this might work, and I encourage you to kind of go and try to answer this question and see if you can use the graph and refresh your memory as to how this is done.